And you must have seen that from what we have read, the integral test requires you a few things, and they're just limited by number. One, it requires you that the function you are dealing with should be continuous. And that is the first condition, that the function you are dealing with should be continuous. Then the next one should be decreasing. Let me say this. You mean you cannot hear me properly? So we have said it should be decreasing. 3, it should be. Zaid, please, can you mute your mic? 3 should be positive. So if you can register those 3, then we can use the integral test to determine what we are talking about. Then probably what should be positive here, we may go further and say that it is the sequence which should be positive. And I'm going to look what you are going to read through the introductory part. And I've told you these are the requirements. Then I want you to look what, including the proof. That is the proof. I want you to go to theorem 3.62. That's where we are picking up from. Other things you are going to read through, then you'll be able to understand. Then since you know I am dealing with the integral test, then you should know that we are supposed to integrate automatically. These are infinite integrals. So it is something simple. So should it be continuous, should it be decreasing, should it be positive, especially the series. So then you go to theorem 3.62, which is on bottom of page what? Bottom of page 46. So what does it say? It is saying that suppose our AK is greater than 0. This is the same as saying suppose our AK is positive. Because being greater than 0, then that is enough to cater for this characteristic of positive. We know that they don't need to tell us where they are picking K, because we said the K is ever picked from N, and that one has been clarified for us. And suppose our function f is continuous. So they have already told us that this one should be continuous, should be decreasing. So we have covered now the 3 characteristics: continuous, decreasing. Then we have seen the sequence is greater than 0, so it should be positive. For which our function f of k equals to what? To ak. So please you follow your handout, because when I share the screen, the problem will be one. You will not be able to edit anything within your work. You will be just writing funny things. So, but you can open your soft copy still. So what I'm saying, what is our FK? Our FK is the sequence. Then we have to show, remember this is what we are interested in, the series converging. So the series AN converges If and only if, we said if and only if you know the meaning, it is two-sided. If and only if integral from 1 to infinity of f of x, this is the dx, exists, i.e. finite. That is the meaning. And being finite, that implies that it is less than infinite. So what does it mean? That sometimes instead of saying that it exists, they will be saying that it is finite. Sometimes instead of saying that it is finite, they will be telling you that it is less than infinity. So those are the things which will happen. And the integration, remember we are dealing with improper integrals. Mentioning this, it is enough to know that we are dealing with improper integrals. Now the questions may arise. How do you determine that the sequence is positive? That is the first question. Because we have already seen that you must call the sequence a function, then you move on. How do you determine that it is a positive? That is the question to think about just in the coming few minutes, because I want the answer right now. 2, how do you show that the sequence is continuous? 3, how do we show that the sequence is decreasing? Because if we cannot confirm these 3, then we cannot integrate. If we can show these 3, then we can go further to integrate. And then if we integrate the improper integral 1 to infinity of our f of x dx, and it is less than infinity. And as we are continuing with the math, some of you who will go for masters and further education, you will see that instead they will be saying that this function here, it is finite, or it is in L1, just L1. They will be telling you why. Because sometimes they will be saying L2, where you have to integrate f of x, but you square it. That will be in L2. And it is in L2 when it is finite. And when is it finite? When it is less than infinity. But here we are dealing with L1. L1 implies you don't square. It will be just power 1. And then to be there, then it should be finite. That is the thing. And it will be finite. Here we are just saying it exists because we are beginners. But the right term should be, it should be finite. Or should be less than infinity. So how do we show these 3? Positive, continuous, and decreasing. Before I go to that, I have to take a note of some few things within your notes. And when you look at on the top of page 47, the test can be used to conclude both the convergence and divergence of a set, unlike other terms. So someone can easily tell you or request you to show or to give a reason why integral test is stronger than all other tests. But this one we can determine divergence or convergence of the set. That's the only reasoning behind. That is the point I was making there. The second point is, we have not said that. The second point is, we have not said that this is sum 1 up to infinity of this is ak, that it equals to integral from 1 to infinity of f of x, this is dx. We have not said so. When you look at our previous work, we have said that what you do, you pick ak, is what we have called our f of x, and then you integrate this guy here, meaning that you are indirectly integrating the sequence. So that is the interpretation. So this one, the sum doesn't equal to this integral here. No, this is not right. So you should not use it. So how do we show that it is a positive thing? One, you remember from your high school math, how do we show that it is a positive? Meaning that if you're having a function f of x, if you're having y equal, maybe if you're having y equals to a function f of x, when do you show that this one here is positive or negative? So what we are going to do, we are going to just look at the first derivative f of x. And if this one here, let's call it 1. If 1 is less than what? Is less than 0, that is, it is negative, then we conclude that the function f of x equals to y is positive. So this is what we are going to do now. We are going to just take the derivative of the function. Maybe if we are having maybe a function f of x is equal to maybe 1 over x. And can you see that in this case, the derivative of this, it will be the same as 1 over x squared. You see, meaning that when you substitute, let's say, x naught, it will be the same as negative 1 over x naught squared. This guy here is less than 0. And since it's less than 0, the derivative, then we conclude that this man here is positive. Hope you have got me clearly. Meaning that as we are testing for positivity of the function, we should use this because this is the simplest. Then how do we show continuity of functions? How do we show that a function is continuous? 1, you use the other original expression, but we may not just go into details. 1, if the limit, when you substitute f of c and it exists, if this one exists, and 2, if the limit as x goes to c of this function f of x also exists, then we conclude that the function f of x is continuous at what? At c, where c is a point. So that is the thing. You conclude that it does what? The point is the point that the function is continuous at what? At c. But generally, this is what we are going to be using. This is what we are going to be using. If you are having, because it's going to be in most cases a product, if f of x is equal to maybe x, we know this one is continuous, that any value of x you are going to get, you get the answer. So it is continuous. And maybe you are having g of x, maybe it is equal to exponential x. We know also this one is continuous every time. So what does it mean? That the product may be p of x, which we can call f of x times g of x. Remember multiplication of functions from your high school level. This is the same as e of x, which is the same as x e of x. This one here, since this is continuous, also this one here is continuous. That is the logic we are going to use. That if this one is continuous, this one is continuous, then you conclude that also the product is continuous. Meaning that you should remember before, as you cover the functions, you said if f of x, g of x are continuous functions, then what happened? Then you said f of x plus g of x, which you wrote as f plus g of x, is continuous. The second one you said f of x times g of x, which you wrote as g of x, is also continuous. This is true with the product of 3, but many are going to use these 2 characteristics. So that is what we are going to generally use. Then the third, how do we show that it is a decreasing How do we show that it's a decreasing function? So you should be knowing what to do with the decreasing. I think you remember that remember that what? Remember how to show that it's a decreasing. You may apply the other knowledge of you may apply the other knowledge of AK plus 1 being less than AK. You remember that this is a sequence, but also you may apply this, or you may apply still the other idea of differentiation. The other idea of derivatives, this one here, it's what I'm meaning. This one here. You still look for the function, you differentiate, you prove this. But I may tell you to reserve this for decreasing, and then for continuous, or for being positive, we may just look at this. We may just apply that if f of x and g of x are positives, then we know that if they are positive, then when you add f of x plus g of x should also be positive. 2, g of x, sorry, f of x times g of x also should be positive. This is the same as addition. This is high school, this is primary work. Positive plus positive, then negative positive times positive, we will get positive. This is high school work. Sorry, primary work. This is the one there, and this one is this one here. So that is the only thing we need to look at. Then let's look at some examples, then we try to move on to something different or better. So examples, we have one. I think let me follow your handout. Yes. Apply integral test. Apply integral test to test for convergence of the following. Let's start with the one you are used to, which is the first example. Let's go with the second one in your work, which is the same as the ke negative k squared. Then the fourth one, what can we take? The simplest, because I don't have the things. Maybe this one here. Let me take the one which is a bit harder. So this is a solution there. Let's try to use the integral test to check for these things, yeah? So that is the first thing. When we go is number 1, which is sum 1 over k. We're going to say let f of x equals to 1 over, or f of n. Can we take x or n? Let's take n. It's the same as 1 over n. This is the thing. We know, we proved already, we know the fate for this. We know that it diverges because we have been proving it from the beginning. So if this is the case, one, we can see that 1, f of x, f of n, which is the same as 1 over n, is decreasing as n goes to positive infinity. How can you show that this one is decreasing? I think you can see, you can prove. You know how to prove this. This one you prove. Because me, I see when I put 1, it will be 1. When I put 10, it will be 1 over 10. So it is decreasing automatically. You know how to prove that this is a sequence now. So you apply what? Apply the knowledge of a sequence. This is a sequence just because we have picked this inner part.
Excuse me, sir.
Please.
Can't decreasing be the same as converging to a certain value, or they cannot use the same principle?
No, because remember when you test for convergence, it implies that it will go to a certain point. But when you prove for decreasing, it may continuously decrease and not converge. And it may continuously increase and not converge. Like when you look at x, this one will continue to increase, but it may not converge. So you should take care. Yeah. Like also x. If you're having x is divergent. It will continue increasing. When you put 1, it will be 1. When you put 2, it will be 2. And put 3, it will be 3, like x squared. But when you put any other value to keep increasing, but it will not, it cannot confirm convergence. So you know how to prove this. 2, we need to show what? And anyway, if you, I think, let me show you the whatever. You can also, but also alternatively, you can also apply for decreasing, because let me show you the one I want you to then use. For decreasing, we use f of x equals to 1 over x, f the derivative equals to negative 1 over x squared less than 0. Then it's decreasing. That is the one we can use for now, because the other one will seem to be harder for you. Instead of this, instead of going to the other side, when you go to the other side, it will tell you that it is decreasing. But this one is better of finding the derivative, because we have said you can find the function, you find its derivative. When you see that it is less than 1, then you confirm that it is, it's less than 0, then you confirm that it is decreasing. So you can apply this to show decreasing of a sequence here. But on the other side, when they ask you to show the other side, you follow the other idea, not this. 2, for positive, for k to be positive, we have f of x equals to 1 over x. Already we have 1. We have 1 which is positive, and also x positive for every n, or for every x coming from n. You see, x is coming from n. It is us changing it to x, because it was 1 over, it was f of n equals to 1 over n. And we said this n comes from n, meaning that all values are positive. So since this one is positive and this one is positive, then f of x, which is the same as positive 1, this, the upper one is positive, the lower one is positive, we get a positive 1 over x. So it is, so f of x is positive for every x coming from n. Now what you put here, is what you should pick from n. So you see, I've picked x. So meaning that if I had put f of n, then I would have said for every n coming from n. If I had put k, then I would have said for every k coming from n. So this one value is what you have picked. So you should take care as you are doing so. So this is, we have already shown the two characteristics. One, we have said that it is decreasing, and I've said you can use this one, which is the simplest, because we are going to be dealing with functions. So you have to, it is easier to differentiate than to go through the other steps. So this one here confirms what? Negativity. Then we have the second one, we wanted to show that it is positive. You will see that 1 is already positive. Then also 1 over x is also positive for every x picked from n, meaning that when I divide, I will get the positive answer, meaning that I will be like picking up the characteristic that a positive function divided by a positive function, I get a positive. So I've confirmed also this one here. What am I remaining with now? I'm remaining with the idea of showing that it is continuous. So since for continuity, we f of x, this is from f of k equals to 1 over k for every k coming from n. Then now look here please. You see that this k is from n, and the values of n are known, that this is the same as 1, 2, 3 up to infinity. You see that these values are continuous everywhere, and there is no value of k when it's going to be 0, meaning that when you say, okay, k equals to 0, you will see that k cannot be a member of what? Of n. So what does it mean? If you get this lower part and you equate it to 0 to see where the function is not defined, it will not be a member of n, meaning that this function f of k is continuous. So some books, what they will be saying, that we can see f of this is continuous. So you should be knowing what to do. But for you should be knowing how to check. Then continuous over n, not over a certain point, meaning that it is continuous everywhere, so long as it is a value picked from n. Now, we can, since ak, which is the same as f of x, is positive, continuous, and decreasing, we have, comma, then we can apply the integral what? The integral test as integral from 1 to infinity of this is f of x dx equals to integral from 1 to infinity of 1 over x dx. This equals to what? I think, remember, you covered this work. It implies that this is the same as when I look at, because I have the upper limit as what? As infinity. I think you remember how to change it to the value you want, which is change of variable, so that we don't directly go to infinity, but we approach there. So meaning that this one will be the same as the limit, as this is maybe t goes to infinity of integral from 1 to t. I think you remember you were changing this guy from there to there, because you don't want directly to substitute in infinity. 1 over x, this is the dx. And this is the same as the limit, as this is t goes to infinity. This one here, when I integrate this, I think I'll get ln. Is it ln x? So from 1 to t. This will be the same as the limit, as t goes to infinity. When I substitute, I'll get ln what? Ln t minus 0, because ln of 0, ln of 1, it will be 0. So what am I remaining with? The limit as t goes to infinity of what? Of ln t. Now, from here we are supposed to interpret the thing. From here we are supposed to interpret the thing. You see, Okay, let's first move with it, then I'll show you something later. Therefore, what is the answer here, please? What is the answer here? What is the answer there when you try to see it properly? What is the answer? Please, what is this answer? Such is if. Such is if. Such is if. Now you are pretending as if you are not hearing anything.
The answer is infinity.
Yes.
Infinity.
Good. This one here is what?
Infinity.
Some of you don't know how to substitute. Okay, good. Some of you don't know how to substitute, but this is infinity. Now you look here. We said that if this one exists, and we said what does it mean to mean exist? It should be less than infinity. But this one here already is infinity, because we said if this one is less than infinity, then we say that it exists. So we say that this one diverges. This is enough to show that it diverges. Since f from integral from 1 to infinity of f of x dx equals to infinity, then our city, which is now from k is equal to 1 to infinity of this is the ak, but this is the same as k from 1 to this is what? Infinity of 1 over k, diverges. Because why is that it diverges? Because we have already seen. Remember we said if and only if, and if and only if the interpretation is clear that if f of x is finite, then this cell is finite. Otherwise, this is when you are moving to this side. When you are coming back, it implies that if the cell now is convergent, then f of x integral exists. But now remember, this is the theorem what? 3.62. Now, this one here implies that 1 over 2, so long as you have this, if this integral exists, then you say this is the finite. But now you have already shown that this one here does not exist. What does it mean? Also, this one here diverges. Because this one here does not exist, that is diverges. Then also this one here should do diverge. That's the interpretation there. So any question up to that point?
Excuse me, sir.
Yes, please. Ogoga, yes. Okay, we are joking?
Sir, I'm saying if we were testing for decreasing and we found that it wasn't decreasing,
then you know you cannot apply integral test. I showed you last time how to do that. Last time I told you, you don't need to continue. You don't continue. But when you are using this integral test, you should be a bit technical. Sometimes, like the example you are going to calculate, the last one, you will see that they will be hiding some components. It is you to think about them. So not directly given to you. So you should be just being keen. But if one of the 3 characteristics, if it is not continuous, you don't continue. If it is not positive, you don't continue. If it is not decreasing, you don't continue. You just conclude and say it cannot be applied here. Like someone can ask a question that why that this question cannot be tested with the integral test. Then you check for those 3 characteristics before you go for the integral test. You first check for decreasing, you check for continuity, you check for being positive. But you use it here, we use only sequence. We use only sequence. So you should be knowing. I think when I talk about a sequence, you know what I'm meaning. So let's go to number 2. Let's go to number 2. So when you try to check out number 2, it is the cell which is given by this guy, K, E, negative K, X. K moves from 1 to infinity. So if that is the case, we can now continue and check for few things here and there. Checking for the conditions. Checking for the conditions. Well, and we know the first one is what? Positivity. What can we start with? Let's start with the continuity. For continuity, what do we have? Is X continuous? Sorry, is the K continuous? We can take f of x be the same as what? X e power negative x squared. Since x and e of negative x squared are continuous, then f of x, which is the product, x times e of negative x squared, is also what? Is also continuous.
Excuse me, sir.
Yes.
Why are you picking x? If I continue with f of k, would I be correct?
It is also okay. It is okay, just because this k and x, these are dummy values. I think when I mean dummy values, you know what I'm meaning, that they are just unknowns. You can use M, you can use the first letter of your mother's name, your girlfriend's name, anything. This is a dummy value. So you are free. I'm using X because most of us, we are used to X. That's the only reasoning behind. But if you are sober enough to use K, it is fine and well. Thank you. So 2, positivity. For positivity of this is A and AK. What do we have? We have f of x equals to, this is x exponential negative k squared. What is the derivative of this? Because we said it's better we use the component of the derivative. We said we use the component of being this. So can you see, Babide, can you see that this is the same as this, x squared e of negative k squared, which is the same as 1 minus x squared e of negative k squared? Babide, can you see that?
Yeah.
Good, you are bright. Can I confirm to you that indeed this one here is less than 0? Otai, can you see that this one here is less than 0?
Excuse me, sir.
Yes.
Why are you mixing the x and the k? I thought when you say that f of x, you're going to replace the k with x.
This is x. It is familiarity. Can you see, Otai, can you see that this is less than x here? That the whole of this expression here is less than x?
Yes.
So if this is less than 0, because for instance, if you can only just look at this part here, because if this one here is maybe 4, you will see 1 minus 4, that one is already negative. When you put maybe 10, 1 minus 100 is already negative. When you put anything you put, you'll find that the lowest will be 0. And if that is the case, then we confirm that it is indeed what? So f of x, which is the same as what? X exponential negative x squared is what? Is it positive? So we are remaining with the next condition, which is what? Which is showing that it is decreasing. It is sorry, this is for decreasing. So f of what? This is what we said for decreasing. It is decreasing. So to show that it is positive, for positivity, we have what? We have f of x equals to, this is x exponential negative x squared, since x and exponential negative x are all positive. For every x coming from n, then what do we have? We have that f of x, which is the same as x times exponential negative x squared, being is what? Is positive. So we can apply the integral test as follows. So this is the next, because we have already achieved the conditions we wanted. So the next thing is to just apply what? Apply the integral test. So, and how do we apply it? This implies that integral from 1 to infinity of this is f of x dx is equivalent to integral from 1 to what? Infinity of this is the x exponential negative x squared dx. And then this is the same as limit as this is t goes to infinity of this is the integral from 1 to infinity x exponential negative x squared, this is dx. I'm expecting someone to mute the mic. Mwonge, can you mute your mic? Mwonge? Good.
Excuse me, sir.
So, yes, Ray.
Yeah, you've said limit as t goes to infinity, but again you brought back the infinity symbol.
This is the t. This is the t, sorry. So what do we get when we integrate this guy here? Which method are we using?
The function and its derivative.
The function and its derivative. Good. Meaning that if you are keen enough, the function and its derivative, you know it well. I think the answer will be what? Negative half exponential negative x squared. This is the answer from 1 to t as the limit. This is the t goes to infinity. Please, what you do, you try this thing out. Anyone who doesn't know how to move from this part, from here to there? If you don't know how to move from here to there, what you do, just apply, just take this one to be your u. You change the variables, you'll find it there. But yours will be in whatever, in u. Then you change everything. You take this one to be u, then you see it coming. There is something I'm going to tell you at the end of this. There is something which is funny there. So what does it mean? Integral from 1 to When we continue with this guy here, it will equal to what? Limit as the t goes to infinity of 1 over 2 exponential minus 1 over exponential 2 exponential t squared. And this one here, when you take a limit, this one here will go to 0. So we shall remain with 1 over 2 of which this one is known. Where E is a numerical, is having a numerical what value. So this one here is 1 over 2E less than infinity.
I hear data when they that's how you get missing marks.
Raymond, you can start from there.
And that is the answer.
Let's go to page 1.
Page 1. Mwalimu mkuu. You would have said the last page.
Guy will come back, guys.
The guy is coming back with the
Wait, let's go to number 3.
So guys, where is the lecturer?
Easy, relax.
I want to go.
As I was saying,
Look at this.
Tell that kid that PLE results were released, so she knows where to fall.
Without even go to school.
Now, you are disturbing. This video is recorded, so you are interrupting, and I don't have time to cut it out. Now, Kenya, you are asking. Please, I want you to try the next number, which is the next example. Check for continuity, check for positivity, and then check for
So first share the screen with second number.
Okay, I'm going to give you. I'm trying to connect with the other device so that we can move together. But for time being, you can try to do for me that number. Check for those few things as I'm trying to connect back.
Friends, on which page are we? All right, thanks.
So you can, I think, look at this. This is the thing. Can you please first look at this expression here? This is what I'm expecting you to use. This is the number 3, right? This is the...
I can't see your screen.
You cannot see it, but it is on. Try to... Everyone cannot see it?
We are seeing, but the words are very small.
Sure.
It is in very small print.
You guys, you can zoom closer.
So I think we are going to... Let's try to move on with this. You should get answer 1, then you conclude that it is convergent, because we are going to get a finite answer. Please, let's stop there for today, because the network is disturbing me here and I cannot connect the other device, so I cannot present.
Okay, sir.
So